Today is, let's see if we're recording here, it looks like we are. Okay. Today we are doing chapter 6, I believe. We're starting chapter 6. So let's take a look at what we've got there. It's all about communications. We're going to do 6.1 and 6.2 today, I believe. And then we will move on to 6.3 on next Monday. And then we'll be back into our projects again. There is homework, so make sure that you check out in your syllabus the homework that goes along with 6.1 and 6.2 is chapter 6, problems 1 through 2. And let's take a look at those homework problems really quick. In your book, they're on page 171. It says, edit the following sentences to improve grammar and style. And there's a lot of them. Well, I don't know how many there are. Like 10, 20, maybe 30. There are 30 sentences. And we'll talk about how to do that in just a second. And then 6.2 is a basic principle of effective writing is to eliminate unnecessary words. The following writing samples were taken from student papers. Edit them to reduce the number of words. Also correct grammatical problems you find. So, essentially we're learning how to communicate. And this is actually a little different than English class. It's actually a lot different than English class. Engineers do not communicate the way English teachers do. Engineers communicate in their own way, which is a very specific, very technical, very concise, very precise, and very short way. They want to get as much information across in the clearest way possible, and on top of that, they want to avoid any kind of confusion or ambiguity that comes along with what English teachers call good writing or creative writing or anything like this. What I'm really trying to tell you is that forget about the thesaurus. If you have to use the same verb 4 or 5 times in the same stinking paragraph because it's the perfect verb to use or the perfect adjective to use, then use it. Don't worry about using interesting words and more descriptive words. Use the best word for the job, and don't worry about what we often do with English papers, which is you don't talk about something being white, you talk about it being ivory. No. Just use the most obvious descriptive word and the plainest one that is easiest to understand. Once we start getting all, I don't know what you would call it. I don't know what I'd call it. But anyway, once we start getting all fancy and English about our words, we actually leave behind the whole point, which is to communicate. So we don't want to do that. And I can't figure out why my screens are not working here. Yeah, I'm not sure why not. I think our power went down, so I think I might have to reset everything. So what I'm going to do is I'm going to turn everything off, I'm going to turn everything back on, I'm going to call you again. I'll see you in a minute. So we'll just leave that as it is. Go into classroom transmit mode. Why won't anything turn on again here? Presentation. looks like we're on track here. Not really all that much to look at. Alright, so anyway, can you see me now? Not sure if I'm going to be able to get anything. Can you see my computer? It should have come up now. Can you see my computer? No computer on the screen? Yeah, we just had a power outage and I'm not sure why it's not coming back up like it should. Let's see if we can make it do that with the remote here. Hold on a second. Now can you see my computer? Excellent. Okay, so anyway, engineering communication is mostly about clarity and less about creativity in use of words and sentences and everything else. Just be as clear as possible. There are also other differences between what we do in engineering communications and other communications. Specifically, we do a different kind of research usually because we're doing technical research more than we're doing what you might call, I don't know, whatever other kind of research. We often have mathematics involved, diagrams involved, lots of data involved, lots of numbers going on, lots of things like this. And so we have to approach our research differently as well as our communications differently because there's so many technical issues involved. And this is something that you'll have a lot of experience with as you go on through engineering or science or whatever you decide to go into. You'll get a lot more experience with communication. But let me just list off. They've got a good two pages I guess, of the different kinds of communications that engineers go through. And we're going to look at some different examples of them. So the first one is technical journals. What is a technical journal? Well, every field of engineering and every field of science usually has several technical journals that they deal with, that they work with. And so let's take a look at the one that I'm probably the most familiar with, which is Physical Review. Physical Review is a technical journal for physicists, and it's been around a long time. In fact, Physical Review is where Einstein was first published when he got his Nobel Prize from it. So here is a really old Physical Review. This is actually the first one, the first issue of Physical Review, and you can see it's kind of bound together over here, probably with staples or string or something like this. Here it's a study of the transmission spectra of certain substances in the infrared, right? And that's actually interesting because that's not that different from what Einstein published. He published a few years later. This first one is in I don't know when that is, but nowadays Physical Review looks a little bit different than that. Let's take a look at what it looks like nowadays. Nowadays, most people read it online, actually. This is what Physical Review Letters looks like now. It comes in a book form, and every couple of months it comes out now. I don't think it comes out every month now. I think it comes out every couple of months. But Physical Review Letters it's kind of the top technical journal of physics. And you'll notice here, if you look at one of the articles, that is a very technical journal. This one is from 19 1981 it looks like, 1961. This is actually from the first collider that was in CERN, Switzerland, quite a while ago. But you can see here that we've got some equations, fairly complex equations it looks like, right? And this is quantum mechanics that we're doing here, particle physics kind of stuff. And it's pretty technical. I mean, you couldn't understand this stuff unless you were in the field that deals with this stuff. It'd take me a good, probably a good week or two to figure out what they're talking about, and I actually worked in that kind of stuff. It's very technical stuff. Notice though at the beginning of this that there is just a lot of writing. So right here it says there is increasing evidence that in inelastic nucleon-nucleon collisions, that one pion exchange contribution plays an important role. Okay? And there's essentially this paragraph that kind of gives an overview of what they're doing. And usually they call that the abstract. And the abstract, nowadays they have a little different format where they actually label the abstract. They say they have a little thing that says abstract at the beginning, and you read the abstract, which gives you an overview of what's going on, and there's usually not much math going on there. Here is an example, kind of an example of that. You can see up here that there's this separate paragraph up here, which is usually the abstract. Let's see if we can find some other ones that are interesting here for physical review. Here's one that actually has the abstract up here, or a summary up here. The Balmer series. Is that? Yeah, this one is a very famous one actually. This is where they discovered the spectrum of hydrogen, and they figured it out and did the math of it. It's the foundation of a lot of things in chemistry and physics nowadays. Let's see, what else do they have here that might be interesting? Maybe not. But they're very technical. The things that you read there are not going to be easy to understand unless you are in the field that it's covering. So here's one from 1939, the multiple scattering of electrons. I believe this is a Nobel Prize actually as well. From University of Michigan, Ann Arbor, Michigan. Right up here, they have their abstract. A theoretical treatment of multiple Rutherford scattering is given, which is exact if one considers electrons with the same total path length and the scatter of the approximation is necessary. This is serious stuff. It's not for your everyday reader. Again, there's mathematics involved and other things as well. It's very, very, very technical type of writing. And it's also very clean. There's not a lot of extra words going on. And if you think there are extra words going on, it's probably because you don't understand the material. You don't understand those extra words, in other words. Oftentimes there are going to be graphs of data. There's going to be scattering stuff. There's going to be imagery. There's going to be stuff within the journal article that tells you what's going on. For example, this would be a very common thing to see in a technical journal article where they actually have some images along with some graphs of intensity here, and so on and so forth. Other things like this are very common as well. Usually they'll have what they call error bars, which tells everybody that's looking at it. Here's an example of this kind of, where it tells everybody the kind of how good your data is. So right here, these little shapes are the data, and then they have these lines that show kind of the trend of the data, which way the data is going, in other words. And so it kind of gives everybody an idea of how close your experiment was to actually accomplishing what you say you accomplished. Just lots of different things going on in these journals. And this is just one type of journal, one type of technical journal. Engineering has its own versions of technical journals. So for example, if we go to IEEE journal, so this is one of the big engineering societies. It's the International Engineering something, I don't know what it is. But you'll notice that they're not very different. Here's one here that has an abstract right at the front. It's even labeled. Let's take a look at that a little bit closer. Here's the abstract. It's labeled abstract. This paper presents the design considerations for a 256-bit bipolar LSI memory component. Excuse me. And the system packaging technology by which the LSI components were assembled to provide 72-bit, 200 nanosecond full cycle main process element memories (PEM) for the ENGR1000 Oct computing system. This computer is actually really quite old. Let's see if it says what year this is. 1970. Yeah. The ENGR1000 is one of the first IBM computers, mainframes. It's quite old. But it was one of the first computers that is based essentially on the same kind of stuff we do now. But here we're talking about this memory that's 200 nanosecond full cycle memory. You know, that's actually fairly slow. Here they talk about many random access memory classification schemes, and they talk about RAM as if it's something new, random access memory. And it was something new in 1970. This was a big deal. They're actually talking about the first use of RAM in a computer, of random access memory, which is essentially computer chip memory. And of course, very, very common today. It's just essential in every computer today, actually. But it's still the same basic stuff. Here they have a table of information, a table of data that they took. They have an abstract. They go through an introduction. And it's very, very organized. So not only is your writing required to be organized in engineering, but since the writing is very organized, the research that you do is going to have to be very organized. And so, above all things, probably, engineers are organized people. Doesn't necessarily mean they're born that way or that they're that way in their own personal life. Usually it means that they've trained themselves to be that way so that they can be effective engineers. That's part of what we're trying to do today. Let's take a look and see if we can see another one. Here's one with a diagram in it. That's kind of nice. So this is again, this is an audio, no, sorry, not audio. This is an analog digital converter. It's essentially a microchip design using all these things over here in this little diagram are essentially what we call transistors. This is what all computers are made of. They're essentially switches. All computers are made of little transistors that have this type of a symbol in a circuit diagram. And they've created a new chip that has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 transistors that are going to be different than this. This is what we call a comparator. And it takes in two signals and compares the two and decides you can do different stuff with it. This is what most of them look like, and they're going to change that up a little bit. So they're going to show another configuration later on probably that changes this. And this is big money because all you have to do really is change one little thing in this thing, just rearrange it one little bit, and all of a sudden you've made your chip smaller, or you've made it faster, or both. Or you've made it work more efficiently with its energy. And usually all three of those things are tied together. Usually faster, smaller, and more efficient are all connected to each other. And this is what a lot of electrical engineers spend their entire life doing, is working with these things and then communicating to the world what they've done. So anyway, that's one of the first types. That's one of the main types of communications that engineers do, is they publish things to journals. Why do you publish things to journals? There's a lot of reasons, but the main reason is so that other people can check your work. It's very easy to make mistakes in your experiment. It's very easy to make mistakes analyzing the information from your experiment. And analyzing it wrong is not uncommon. So you think you did one thing, you actually did another thing, but you messed up somewhere in between. And the best way to have it checked is to show people what you've done without telling them step by step what you did, and having them go out and try to do it from what you've told them. And if they can go out and do it, then it's an easy way to verify that you've done it right. If they go out and do it and then discover something different, that's a really easy way to figure out if you've done something wrong. You go back and check your work. So that's the number one reason that people do this. Another reason is because of competition. These journals, especially the high-end journals, like the first one I showed you, Physical Review Letters. There's another one out there called Nature, which is a general science magazine, a general science journal. It's almost a magazine. Difference between magazine and journal is magazine is for the general public. You know, it's kind of written for everybody to be reading, and a journal is written specifically for people in a field. But Nature has kind of come up as this place where people like to put their discoveries first, so they can be the first one to do it. It's competition. And so they'll compete with, you know, these scientists will compete with each other, and engineers will compete with each other to be the first one to publish that they've done this. Well, of course, if you publish that you've done it and nobody checks your work, then you're kind of in trouble. Or if they check your work and it's wrong, and that's one of the problems they have these days, is they have scientists that publish their work with public magazines, and they don't necessarily have other scientists checking their work. And that's happened many, many times. The most recent big problem with that was probably the whole fiasco with global warming. All these scientists did this research, and then they never reported it to the journals. And it was found out just recently that they actually made it up. That's why they didn't report it to any journals, because if they made it up, then you can't really test it, right? So that was a big stink a few years ago, and it was kind of hushed up because nobody wants to admit that when it went on in the science community. But several professors were fired. One specific professor in Sweden, I believe it was fired for making up all this information. And a lot of politicians have backed off their support of these global warming issues, like solar power. It doesn't get much interest in Congress these days. Even wind power is losing support in Congress, because all those technologies got their start with this research saying, well, if we keep burning oil, our entire Earth is going to melt. Turns out that there's nothing to back it up. The research is flawed. Not only flawed, it was made up. And so that's the problem with science, though, is that if you don't have somebody checking your work through one of these technical journals where other scientists are reading them and other scientists are checking them, then you get fraud, a lot of it. You get a lot of fraud. Very, very unlikely that two scientists are going to lie about the same thing. It's rare to find two scientists that are willing to put their entire life on the line through this. So anyway, lots of different technical journals out there. The next thing that they mention are books written by authors who are familiar with the field and they want to give a more broad or a more detailed explanation. And there are just hundreds and hundreds of books written by authors on specific topics. When I went into atomic physics as a graduate in graduate school, I was given a book called Laser Cooling and something or other. Laser cooling. And this was essentially my class, laser cooling and trapping. This was the first book written on this topic of laser cooling. And it's not really a textbook. It is kind of a textbook, but it's not really a textbook. Really, it's the first comprehensive guide to trapping atoms using lasers. And my job was to buy this book and to read it, and I had to solve a few problems, but mostly I just needed to read it all through, and that was my class, because everything that we were doing in our laboratory had to do with laser cooling and trapping atoms. And the two people that wrote this were two of the people that were really working on this field at the beginning of this, when this field was born. Harold Metcalf and Peter Vanderstraat. So I read the book. I learned as much as I could about laser cooling and trapping, and I kept it around because it's a great resource. It's not even that big of a book, but there's just tons of these books out there in every field of science. So, for example, if I was going to go into let's say mechanical engineering, And I wanted to know something about muscle wires, for example. I might look up a book on muscle wires. And right here I've got, this one looks like it's a muscle wire project. It looks a little more like a kid book. In fact, I have that book. It's more like a book for just playing around with it. I'm not finding one here. Let's do a book on muscle wires. There's got to be one out there somewhere. Anyway, muscle wires, there's probably a more technical term for them, and I just don't know it. Let's look at let's search for something different here. So let's say that I've got to learn about the kinetics of materials. And so I need to learn something about that. I want to go here and look up this book here, The Kinetics of Materials. Most of these books don't have very exciting covers because they're written by scientists writing to other scientists. They're not trying to impress anybody with their pictures. Most of these people all know each other. So in this case, this guy, Balufi, man, he could have a better last name. Balufi, Allen, and Carter, obviously 3 experts in the field of kinetics of materials. Okay. So these books are often written, and there's many of them out there. And usually you want the newest one you can get, because one that's 20 years old may be completely outdated and obsolete. And so you usually want to get the newest one you can get from the latest people working in the same kind of stuff you're working. Conference proceedings is the next thing they talk about. In conferences, something I may have mentioned before, but I can't remember. But engineers and physicists and scientists and mathematicians, they are constantly going to conferences, it seems. So let's look at APS conferences. Conference 2014. Let's see where it is this year. APS full meeting in March. It's in Denver, Colorado. Dang, I need to go to that. That's close by. Denver, Colorado. And that's a good place for it because it turns out that just south of Denver is, there's some great universities just south of Denver, just north of Denver, and in Denver. And so they'll be able to pull in a lot of people, and that's great. But every year, the APS, which is the American Physical Society, has a great big meeting, and thousands of people show up, students and professors and researchers, and great, they show up to this thing, and it's just the biggest nerd convention of all time. It's even bigger than those big, what are those ones where they dress up as like cartoon characters and people in video games? I don't know what they're called, cosplay or something like that. But they're even bigger than those things are. And they meet every year and get together and they talk physics. And they have sections that get together that are meeting to talk about the same kinds of science. And they have poster sessions where people can make a poster and explain what they're doing. And they have people that are selling stuff there, a huge convention center. I mean, it's a big deal. And they have exhibits being put on, and they have all kinds of activities for people. Here, let's look at the events and activities, because I didn't know this was in Denver, so I got to figure this out. So they have information booths, stuff on social media. They have some tutorials going on. They have a short course in multi-scale computational approaches for simulating polymers from atomistic to mesoscale. Wow, cool. And then they have all these sessions where people are going to give talks. For nearly a week, they're giving talks. So that's huge. But engineers have them as well. It just so happens that one of the engineering societies I belong to is having theirs in Florida this year. And I was thinking, man, I'd love to go to Florida in December, because it's in December or January or something like that. That'd be sweet, but I can't afford to go. But every time they have one of these meetings, they record everything that goes on. They record, they take video, they take audio, and they also take everybody's abstract, because everybody that does a talk has to give an abstract on what their talk is about. And they publish all this stuff. They put it all onto discs and onto little thumb drives and to all kinds of things, and they hand them out to everybody, and they make them available to everybody. So all the stuff that's going on right now is available for people to look up. So if you learn something cool at this meeting, or if you missed the meeting, you can look it up, and you can do your research there. Conference proceedings, they're going on all the time. There's always a scientific conference somewhere. And they go on all over the world. And that's one of the cool things actually about being a scientist or an engineer, is that oftentimes, most of the time, when you work for a company or you work for a school like me, they actually will pay you to go to these conferences. I've been to maybe 5 conferences since I've been here at the college in 6 years, and actually probably more than that, probably more like 10. And every one of them has been paid for. My travel was paid for, my food and board, room and board were paid for, and the conference was paid for by the college or by a grant. Most of mine were paid for by grants, and that's why I don't have any more. I've been traveling much because I ran out of grant money. But, excuse me, if you work for a company, they will pay you to go to these as well, because they want you to be informed, they want you to meet with other scientists and learn as much as you can. And it's kind of nice. You get paid to travel. If you enjoy traveling, that's great. My brother went to he went to a conference recently in Italy, I think it was. I mean, oh, great to be paid to go to Italy. I love it. My dad got paid to go to these things all over the world as well, and I've never been to one outside the country, but I've heard they're fun. But that's not true. I went to one in Canada. I guess that kind of counts as being outside. So, conferences, conference proceedings. Of course, there's online stuff. Here they talk about encyclopedia articles. Mostly you don't talk about encyclopedia articles anymore without talking about online stuff, right? Because mostly we're talking about wikis or Wikipedias. But there's also all kinds of other things. The government does tons of research. Energy, the Department of Defense, the Department of Interior, the Department, all kinds of departments do all kinds of research and publish their results as well. And then they list patents. That's the last one that they list on page 147. And you said, well, wait a second. You already talked about scientists and engineers publishing things. Why would they publish or do a patent or not do one or the other or do both? Sounds like the same kind of thing. It is kind of the same thing, except that it doesn't cost anything to publish. When you send in a publication on some new thing that you've done in engineering or some new thing you've done in science, they don't charge you to publish it. If you're a member of their society, you can publish it. So you have to pay for the membership. And it has to be good enough, because they're going to only take the best papers and the best articles that they receive. The ones that they don't think are very important are not going to be published. How do they decide that? Well, there's a group of your peers, a group of engineers that they send the articles to, and they say, rank this article. You know. But and that process can actually be fairly long, and that's really the difference. You can publish your things, but it's not a sure thing. But it doesn't cost you any money, so there's a gamble. It also takes a long time. However, if you patent something, you don't have to go through the process of having it peer-reviewed. It doesn't have to be looked at by your peers. You don't have to go through the long time process that it takes, but it does cost a lot of money, several $1,000s in most cases, to patent something. So you can either get credit for it through the publishing process or get credit for the patent process. Essentially, the end result is the same. If you publish something and you were the first to publish it, and it's easily proved that you published it, and then somebody tries to patent that, they will not be granted that patent, or you could challenge their patent, because it is your intellectual property, and you came up with it first and published it in such a way. You can't win a patent process. You can't win a patent or argument or a patent lawsuit if you don't have something published somewhere. Usually, you can't just say, "Well, I've been doing this and I wrote it all down," or "I told my best friend," or "I started making this thing. You know, if you invent something, for example, a friend of mine brought me something that he's invented essentially, and he wants to patent it, but it won't count unless he patents it first, or he publishes it somewhere. And so essentially you have to have some proof, and it usually has to be some kind of written proof that you invented it first, and then you can argue it. But anyway, patents are important because it does give you that legal right to make money from something that you invented. And you'd be surprised what some people patent. Let's take a look at an example here. Let's go back to Google. Where's Google? Google. So the best example of patenting things, I think, is Apple Company. So let's see. So there was this huge story on Samsung where Samsung violated Apple's patent, and it's kind of interesting what it came down to. So here's Samsung's phone. This is the one that you can't buy in the United States because of this patent law that Apple won. And you may or may not understand what, you may or may not have heard what, really. What was the problem? But the real problem was actually these little pictures on the front screen. Okay? And we can actually show you a better idea of what's going on here, probably, maybe. Let's take a look at different search. So here's what it comes down to. Oops. So, ornamental design of the phone. What the ornamental design means is that how they set up their screen, essentially. The icons have a rounded edge, a rounded corner to them. They patented that. They patented the look of the screen, patent 087 and 677, and there's some other numbers along with that. And then they patented the actual rounded corners on these things. Can you believe that? They also patented a bunch of multitasking gestures and the way that things come in when you're multitasking, right? So you've got multi-finger gestures and the look of the phone, essentially, what it comes down to. But the biggest thing was actually this one right here, the rounded square icons. These little squares that tell you what you're going to look at, what you're going to open up, have rounded corners. Can you believe that you can patent that? And Apple patented it first. They were also the first ones to develop a phone that does anything like this, that's anything like this. And so nobody could say they did it first before Apple, because Apple made the first true smartphone ever. First touch phone ever as well. So it's kind of interesting, and they won the lawsuit. And now, if you pick up a Samsung phone that has whatever operating system, whatever Google operating system was on there at the time, it will have different icons than those. Simple enough. Crazy. Yeah, actually. However, how can patents be used by engineers? Well, of course, they can be used to protect their intellectual property, but they can also be used to learn things. So if you're trying to design a new kind of cell phone, it'd be a really good idea for you to go onto the patent website and figure out what Apple has patented already, so that you don't use something that they use, that they've already patented, even if they don't use it. Because if you use that thing that they've patented in your new phone, they're going to sue you, and you're going to lose, and you're going to probably lose your company. Samsung didn't lose their company because in the Far East, where Samsung does most of its business, believe it or not, they sell far more phones in Asia than they sell here. The Asian countries don't care. They don't care that they violated the patent, and they don't hold them responsible, so it doesn't matter. It's actually one of the biggest international law problems we have in the world today. If United States companies were reimbursed for all the things that Asian companies stole from them and used against contrary to patent law, we would easily outstrip China's national income. We would have so much money in our company, it would be ridiculous. But they don't. They refuse to recognize our patent laws, even though there's an international treaty saying that they have to. But China's always kind of done their thing, so. And nobody wants to get in a fight with them over it. Okay, other things that you can use to learn from and to also describe your work. You can use popular magazine and press articles, newspapers, news agencies, you know, to Newsweek Time and other things like that. It's not a very good way to try to connect technically with the world, because it often there's a lot of things lost in translation. But sometimes it's useful. Also, you can go back to your courses, the things that you learned in your classes. This is why most engineers and physicists and other scientists keep their textbooks, and they keep their notes from their classes often. I just barely got rid of most of my notes when we moved over to this new building, but I kept some. And then also the internet. Lots of things you can learn on the internet. Libraries, of course, are a very, very useful tool, but it turns out that there are very few libraries left anymore that have technical information that's useful to engineers, unfortunately. Most of that stuff has been digitized, and it's now available online, which is the fortunate side of things. Now it's much more convenient to access that stuff. The problem with that is that since there's so much junk out there, it's often very easy for people to manipulate that stuff as well. And so you don't always know if you're seeing what you think you're seeing. Okay, so, excuse me. We didn't quite get through everything, and we're just about done here. In the last part of section 6.1, we'll cover 6.2 and 6.3 next time. But in the last part of 6.1, they talk about organizing when you're writing. It's extremely important to organize while you're writing. And so I might actually spend a couple more days doing communication than I thought I would. But we will talk about different ways that you can organize your information when you're about to write something or you're about to give some kind of communication. So not written communication, it can be some kind of spoken communication or whatever else. But you should always have an organization structure that determines what goes where, when, and why. So we will cover that next time. Make sure that you know that there's homework in the back of the book. And that homework won't be due until next week when we're done with Chapter 6, so you've got lots of time to deal with it. And we'll see you later. Have a good weekend. I don't have anything else for you.